Well, thank you, Mike. Well, thank you all for being here. I've had the honor of working with Michael Sprinkel for the last 12 years, nearly 12 years of his career slash life, because that was his life, right?
He helped to hire you,
Yes, yeah, he.
and you are doing wonderful.
Thank you, sir. And just a little information thrown in there. Virginia Transportation Research Council celebrates the 75th anniversary this year, and as you can tell, Michael played a huge role in what the council stands for and what they accomplished. So I thought I would talk about kind of an example project, a case study in a way, which is still quite relevant because I worked with Michael Sprinkle closely with this project in 2015. Honestly, it's really quite relevant today, and the project was more than 3 or 4 years long, and I learned so much. I thought this would be a fun kind of project to talk about. These are two bridges here, fairly long. One of them is a mile long, another one is two-thirds of a mile. One of them is a movable bridge, as you can see at the bottom. There's a movable section. And the other one at the top is basically the same design without the movable span in the middle. And on both these bridges, they're only about a couple of miles. They're situated in a marshy environment. You have two big, massive rivers, and there are four sets of post-tensioned beams, spans. Essentially, there are four spans on each side of the movable span, same type of design on the top bridge as well. And these were only built in 2006 or 7, and they started showing some problems in 2015, so within 10 years. Just to show the profile, the four spans are continuously post-tensioned. And you see they're totally about 880 feet, so fairly long post-tensioning there. And these are the cross sections of the girders, fairly tall girders, about 8 feet tall, but in the web is about 8 inches, so fairly slender looking structure. And this was one of the first lightweight concrete girder systems that we had in Virginia for such an application. I think the expected strength was 10,000 psi. Fairly successful application. As you can see, there are three little circles in the web. It's a thin web, 8 inches wide, but then you have ducts about 3.5 inches right in the middle. So there's not a whole lot of concrete around it, right? It's taking a lot of stress in there. And in 2015, the inspectors found huge concrete spalls around these ducts. And you can almost see the duct kind of exposed right there. And this was found on the fascia girders on a few spans. And there was a huge concern, what's happening here, right? And there were also a bunch of cracks around the web area, as well as a little bit on the flange. And you see some moisture kind of leaking out as well from these cracks. So the district people panicked. They contacted Michael Sprinkle because Michael has always been the expert on grout, anything grout. So they wanted to know if this is related to anything that's inside the ducts. And Michael had so much experience prior to this. So this is kind of a compilation of his previous study in the early 2000s, where he made a matrix of grout samples just to see what happens if more excess water is added to the grout. I mean, how does it behave? Does it just become porous, holds the same volume, or does it become soft at the top, and there's water at the top, and then solid grout at the bottom? So he had a bunch of these tests, lab tests done, and it was published. So he went back to look at the data. As you see, there's the x-axis is the amount of water in the mix, and then the y-axis is the change in the height. This is supposed to be 8 inches tall, by the way, the concrete. And then when they added like 0.65 water to binder ratio to this grout, It was only about 6.5 inches tall. The rest of it was soft grout at the top. You see a little bit of it, and the rest of it was basically just water, just leaked out. So he suspected, based on his experience, that maybe that's what happened. Maybe it was excess water must have been added during construction. That was one of his hypotheses. And why did the spalling happen now, not 8-9 years prior? And that was a really cold winter. So he thought maybe it has to do something with the freeze thaw. If there's excess moisture sitting in the ducts, maybe there was some freeze thaw that caused the expansion of the grout, which could have kind of pushed the web out. The web is only 2.5 inches wide, so not a whole lot to hold it in place. And then he also thought maybe, depending upon the type of grout used in this bridge, his expectation was the good grout basically settled down, while there's a transition layer of soft grout, moisture, and then big voids at the top. So we wanted to just check each of these. He went about, like Mike Stenko was talking about, he's all about simplicity. Just do something. Just don't keep thinking about it. Just do something, right? He just took a big concrete cylinder, 6x12, with the same grout composition, and then put in a 3.5-inch conduit inside with a bunch of water, and then just froze it overnight, and then it cracked up. He thought, hey, that's a problem, right? That's the most likely problem. And we went ahead and planned a fairly large field study. I only had like 3 years at the council back then, so I was basically his grad student. So he took me along, and this was one of the best experiences I've ever had. And this is a fairly tall bridge, and there's a bridge, a huge water body below. And there's a paper mill right in the middle of these two bridges, so there's lumber trucks all the time, like 24 hours, right? So on a bucket truck, you feel every time there's a timber truck going about. And these are 240 feet each span, so the displacement was as much as a steel structure, so it's fairly flexible. So we looked at a bunch of cross sections. I was just learning some non-destructive testing. That's when I had a chance to implement some of those learnings. And we looked at 54 cross sections on one of the bridge and about 26 on another bridge. And this was on all gutters, and then here just the fascia gutter. And he decided to open up a few spots, because just having the NDE wouldn't be enough unless we can look at the ground truth comparison, right? So we opened up 41 plus and looked at all kinds of composition. Was a chloride in there, sulfate in there, what the pH, because if the excess water was added, then the gypsum would have segregated, and that would show up as sulfates, and maybe some change in the pH as well. And we looked at impact echo. We looked at about multiple technologies, and that was the one that worked out well in a small mock-up we tried in the lab. You know, he really likes to prepare, really be prepared for field work. Every minute we spend in the field costs money. You know, there's traffic control on lanes, there's renting of special equipment, so he wanted to make sure we use that time wisely. And as you see at the top left, we opened up a suspect spot after doing some NDE, and we saw some little bit of water leakage. And he thought, hey, I mean, the water leakage is fine, but then it doesn't seem to be as much as we thought. And then we looked at another couple of spots, and then he decided, maybe the settlement of this grout is not as uniform as one would think. Maybe it's all over the place, because they're trying to push this grout through this entire 880 feet long duct, so maybe it's all kind of all over the place. So he decided to, on one of the next runs of this field work, he brought a air compressor, and then kind of pushed all the concrete out. And here I would like to show you. This is, I wonder if I can run the video. This is before, oh, wait a minute. This is after the air compression. That is Michael Sprinkel, by the way, drilling into the post-tension duct on the bridge there. See the water gushing out? We must have found gallons and gallons of water. We were totally unprepared for such a large amount of water in there. But in the next gutter we poked into, we were able to get a bunch of sample from the water, right? I mean, you see water still coming out. It's not done. So this is gutter 3, pier That's me
34,
recording the
and span II.
ID of the location.
we drilled up there.
Yep.
You know what?
Yep, that was Michael's voice, by the way. That's why I left the video running. Here's another kind of a ridiculous amount of water gushing out. That's like a pipe. That's from a nearly 10-year-old structure.
Touch that game.
As you see, this is only about 35 feet from the pier, so the duct is kind of going out, right? So you have all the water just there. So we found the most critical part, and the water was like, we could have filled a 5-gallon bucket with it, with each spot. That's right. That's his glasses, by the way. So some interesting observations. Even the interior gutters had a ton of water in them, even though they looked pristine. There was no cracks. There was nothing at all. But then the NDE allowed us to see what was happening in there. And we realized that the temperature difference on the outside gutters, it's much different from what the interior bay gutters are experiencing. They're not going through the ups and downs as much as the exterior ones, so they didn't crack as much, even though there was as much water as the outside gutters. And one of the things that kind of stumped us was one of the bridges was quite predictable, like the solid grout at the bottom. There's a transition layer, and then there's not kind of a void at the top. But then the other bridge stumped us too, because it was we found some void at the bottom in some areas, and then some solid grout at the top. So they must have really pushed that concrete grout through while it was setting. So there were multiple mistakes being made at this construction. And he also wanted to make sure that the water didn't come in after the construction, because we set up these ponding on top of the deck on the location of cracks. It was dyed with red dye, and then was basically using air compressor. We tried to pull in that moisture, and then we were not able to see anything. So the conclusion was all the water in there was from the time of construction. Nothing had come in after that. So that was kind of a relief. So right now, plenty of work has been is ongoing. One of the issues we found was, even though the NDE was hugely helpful, he wanted to make sure that we had multiple options in terms of technologies, because all technologies, they have some pros and cons, and it's easy to miss stuff, especially when you have so many cracks on the surface. The impact echo that we used did not help to look inside. It would kind of scatter the waves and wouldn't really see inside. So that was him finding a digital gamma ray radiography, a medical device, basically. He made some mock-up specimens and put in different types of defects inside the ducts, and used this digital plate to record the readings. And this was some of the best readings we have ever had with NDE, even though it's quite expensive, at least back then, and it's close to how it actually looks like inside. So what you see is kind of the representation of the density. The darker something is, the less dense it is, and the brighter something is, the lighter, the opposite. Okay. So you see the strands, you see the void in the bottom. This is the plastic duct. This is a metal duct. No difference. You see even the corrugations of the metal duct. It was the most impressive technology we used back then. And this is another one of his ideas to use mock-ups on all these exploratory technologies. He wanted to make sure absolutely that something would work in the field, and then the time in the field is money, as I said before. So that is an external tendon, what Chelik had showed before on a signature structure. He made a mock-up of it with a bunch of defects placed inside, and then that's the consultant running a magnetic flux leakage on it to find out all the problems. One of the main takeaways is the amount of preparation that he, the importance he placed on them before heading out. As you can call, it's a triple blinded nature. Nobody knows what's in there. The owner doesn't know. The consultant doesn't know. We have no idea what to check this against. So we need some limited ground truth is all we can look for. And there were two other instances where some of the NDE methods did not come through. We've only found about 60% match with the ground truth that they had a vast amount of data was collected. Another investigation only found about 50% match. And a magnetic flux, one consultant had 100% match, and another only found 60% on the same exact mock-up. But then he did not want to give up on the same theme. He did not want to give up, so he made sure we would accept people who can qualify based on the success of their demonstration, not based on a technology. He didn't want to say no to a technology. He just wanted to say no to someone who did not pass the test. And that's what VDOT has been using ever since. It's not just NDE, structural monitoring has the same thing. And that was all his ideas. In takeaway two, there was common sense over anything and everything. No amount of AI or machine learning can compensate for the lack of common sense. He really believed that. And do not harm. And he did not want to poke holes into bridges unless it's absolutely necessary. He didn't want to introduce anything new, any new harm to be done to the bridges. So that's why he was a big proponent of non-destructive testing and structural monitoring, and he never really gave up on them. And the final takeaway, learning by doing. I mean, that's him. He had over 40 years of experience by then. I'm the one taking the picture. I had 3 years of experience. He wouldn't let me drill that thing. He wanted to make sure that that's done right, because that was the first time we're attempting something. He had an army of technicians, and he could have had anybody help him out. But he wanted to learn by doing, and that's the biggest takeaway for me. So it's been an honor working with him and learning from him, and we'll always miss him. Thank you.